I'm Osama, and I'm here to present our work that highlights an important problem that hampers the web experience of users, especially from developing regions. This is a joint effort with my advisor, Theo Benson from Brown University and Ravi Netraveli from UCLA. Okay, so memory problem in webs are quite common, and I'm fairly certain that everyone in the audience has faced one of these problems at one time or another. Now, the common theme with this problem is that it's quite straightforward. Like either the browser or some part of website like JavaScript consumes too much memory, the device runs out of memory, and the user complains. Since better quality of experience leads to better revenue, content providers are working hard to improve web experience. In the recent past, we see efforts to improve network infrastructure, website code, and optimization for hardware resources like CPU and battery. However, we observed that that memory resources didn't really get their fair share of attention. There are a number of interesting questions that are unanswered, like how do memory constraints impact web performance? How much memory does a typical user device has? And what are the expectations from common websites in terms of memory requirements? Now, this problem is especially important for low-end devices, since although memory as a hardware is cheap, it is limited and it's unupgradable for mobile devices. So content providers are kind of stuck with this limitation, and they need to optimize whatever they have for these devices. So the rest of the talk is structured as follows. I'll start with describing the impact of memory constraint on web. Second, I'll show that the low-end memory devices are still very common in developing regions, and the websites are not actively catering for the unique memory landscape. Third, I'll talk about how we can optimize memory consumption in web and present our vision for the system. Finally, I'll shed some light on some future work and conclude. To understand the impact of memory, we built a test bed with multiple mobile devices in 1 to 4 GB RAM range. Besides popular manufacturers like LG, our test bed also had a device from HotMobile, which is a popular manufacturer in Pakistan. We picked 50 websites individually from 5 different regions and recorded a regional version of that web page. These websites were later replayed and loaded on Chrome browser in a clean state. That is, there was no background app or tab running. We further conducted some stress tests where we restricted the amount of memory available to the browser. Our goal here was to measure memory usage for popular websites as well as OS events like garbage collection while loading those web pages. Now, unlike traditional Linux, Android does not have virtual memory and instead relies on garbage collection and out-of-memory killer to make more space for a new process. So at a high level, we see two implications. In the bad case, the OS is able to reclaim memory through garbage collection. However, there's a cost associated as the application is stalled and precious CPU cycles are consumed. We observe up to 2.6 times higher stall time for the low-end device as compared to the high-end one. Now, this stall time since the browser is stalled, this stall time reflect directly into the inflated page load time. In the worst case, the OS is unable to reclaim memory, and that leads to the case where the device is out of memory. As a result, the foreground application is killed, leading to a browser crash. In our stress test, we saw that when the total memory usage exceeded 90%, there was a crash. Next, I'll share some measurement results to show that it's the users in developing regions that mostly suffer from these negative implications. Now, in order to sketch the landscape of device memory resources in different parts of the world, we collected data from global social network. Our data set spans all the major continents and covered more than 4 years, from 2015 to March 2019. The data set comprises logs captured from Android devices that install the app, and the logs capture device model, hardware specs, and geolocation. Note that the app only collects data from the user that have explicitly given permission. We further classified the region into 3 categories based on United Nations economic classification and classified the devices into 3 categories based on their RAM. Now, let's see how the resources have evolved over the year in different parts of the world. The figure here has year on the x-axis and RAM in GBs on the y-axis. Each box here shows the memory distribution for the unique devices that were seen in an year. For the developed regions, we see that there's a consistent increase in memory resources with time. In 2019, the median device has 2 GB of RAM and the tail one has as much as 6 GB. For the transition region, we see a similar trend where the memory has grown over time, although the rate is a bit lower. However, for the developed region, for the developing region, we see that the trend is a bit different. We have two takeaways from this figure. First, the memory resources are kind of stagnant across the 4 years. So the median was around 1 GB in 2015, and it's still around 1 GB in 2019. And the second is that the rate at which the memory has grown is a bit different. So we see a gulf in memory resources when we look at devices in 2019. There are socioeconomic reasons for why these devices have low RAM, because most of them are budget. The budget devices are kind of popular in developing regions. And we also see that there's a higher degree of replacement, where people tend to use their devices for a much longer time in developing regions. So the older ones are still in operation there. Now, one would expect that this discrepancy of resources would reflect in the memory usage requirement from the website. However, as in reality, expectations can hurt, and that's what we see in our measurement. We see that a typical website in developing region actually consumes more RAM than a one in developed one. This results indicate that the users in developing region disproportionately get impacted by the negative implication of their special landscape of memory resources. Now, if you put these two measurements together, we see that even in 2019, around 20% of devices in developing region has less than or equal to 512 MB RAM. Our measurements show that for these devices, only 52% is available for an application, and the rest is taken by the OS. Now, when we put the website's memory usage into context, we see that a single website in a single tab can take somewhere between 23 to 94% of RAM. And this is huge, since it's only one website. There is no background application or anything else running. Next, I'll talk about what we can do to solve this problem. I'll shed light on some design choices and our vision for building a system to alleviate memory problems. Now, the first option is to optimize or rewrite the OS to fit the needs of the low-end devices. And we do see it in form of Android Go, which is a lightweight version of Android. However, there's two problems here. First, although the OS footprint is itself smaller, we see that the website still consumes the same amount of RAM as in the regular Android device. And the second problem is that there are network costs associated with delivering over-the-air updates. And for some cases, due to the out-of-date hardware configuration, these updates might not be even possible. A second option is to offload JavaScript, which is typically the culprit behind high memory usage. So Opera Mini does that. It offloads the JavaScript execution to a proxy. But during our test, we saw that it leads to personalization problems, since the JavaScript is not running on the user device. We also saw that there were pages that got degraded in their appearance or in functionality when Opera Mini was used. Another option is to use specialized frameworks like AMP that use resources more conservatively. But this assumes that the developer will rewrite their services using AMP frameworks so that they consume less resources, and it puts an immense burden on the developers, and that's why we don't think it's an ideal option here. Last but not the least is browser optimizations. For example, in Chrome, we see optimization like heavy ad interventions, where the browser terminates JavaScript execution if they see that the device is running out of RAM. But our measurements show that these interventions are not enough. So this figure has JavaScript memory on x-axis. And for this figure, we classified the JavaScript into three categories. One was JavaScript fetched from cross origin. The second is ads, and the third is trackers. So what we see here is that for the median case, ads and trackers do not significantly impact memory. There's only a small number of websites at tail that do have significant ads and memory-related memory overheads, ads and tracker-related memory overheads. But for the median or for the rest of the website, it's not significant. Now, one thing that's common across our measurements and the analysis of optimization is that JavaScript is the prime culprit. optimization that play around with JavaScript, either by limiting their execution or by offloading their execution to some other place like a proxy, do have significant memory savings. So the idea is to just remove the JavaScript content to save memory. So if a website that is a bag of JavaScript, we can remove some of it for the low-end device, and that's it. We can pat ourselves on the shoulder and go home and celebrate because the problem is solved. But there's a lot that can go wrong here. So it turns out JavaScript has a utility value. There's a reason why people use it. So there's calls like add event listener, where you can add some functionality to the page or the JavaScript and add images, change CSS rules, and do tons of other stuff. So if we are removing JavaScript, we are effectively removing all this functionality and visual appearance related utility from the web page. We have also observed that, as I said before, that removing ad trackers and cross-origin content is not enough. So we need to actively cut same origin content that is deemed to be important for the page load. So we are kind of a situation where we have two extremes. On the left side, we can keep all the JavaScript and all the utility, but the page might crash. On the right side, we can remove all the JavaScript and all utility will be removed, but we'll be kind of left with a page that doesn't work. It will be kind of this hammer with chain that has no utility. So the key here is to find a point in between where we trade off some utility and get some memory saving. And that is the exact idea behind WebMedic. Our vision is that a less functional but working page is better than a crashed one. So WebMedic performs a surgery to trade off less useful utility for performance. So assuming we have a page where the index references some JavaScript, we can assign a utility value to the JavaScript, and based on this utility, we can decide what do we want to keep, what will be more important to the user. We can cut the rest and create a low memory version of the page. Now, the design of JavaScript, the design of WebMedic gives rise to some very interesting research questions. The first one is that, can we arbitrarily cut JavaScript? And turns out we can't, because JavaScript has state dependencies. For example, in this example on the right, the script in the head defines some state that is later referenced by some other script in body. But if we naively cut the script in the head, it will lead to problems for the script in the body because the state doesn't exist. So, but we do know that JavaScript execution is sequential in a browser. So the browser executes the JavaScript per iframe in a single-threaded manner. And we leverage this behavior to sort of make dependencies between two JavaScript with the assumption that a JavaScript that runs after the other one may have a soft dependency in terms of state. So using this heuristic, WebMedic first decomposes a website into its bag of JavaScripts and creates a dependency graph. The second question, and the most important question, is how can we evaluate a cut? As I said before, there's a utility associated with it, and in order to evaluate the cut, we need to measure how much utility we actually lost. So right now, for functionality, we measure the number of event handlers, and for visual appearance, we use perceptual hash, which is like a fingerprint for a screenshot or an image that can be compared with another fingerprint to measure how similar two images are. So currently, we do this in an iterative way. It's an offline process where we cut a JavaScript, we load the web page in a browser, and we take a screenshot, DOM properties, and memory usage. And we keep doing this for each JavaScript one by one, and we compare it with the baseline to measure the utility and memory profile of individual JavaScripts. Now, the third question is, who makes a surgery? We don't want to put this burden on the device itself, since it's already low on resources. So currently, WebMedic works as a server extension. It intercepts the HTTP request and headers, and it uses the device user agent string in the headers to find out about the memory, resources of the device and cluster it based on that. It uses the HTTP request to sort of calculate what dependency resolution it should use for the website, and then it has a decision to make whether it wants to exploit an already seen cut or whether it wants to explore something new. So Based on this decision, it serves in the optimized version of the web page, and the user has the option to say whether they like the page or they don't. And these results are fed back to our model to refine the decision. Note that we also use the offline profiles in the exploitation step to create a set of contender cuts that should be tested for page load. Now, in our preliminary evaluation, we tested 250 websites from 5 regions. And using the iterative process, we performed a brute force cut where every JavaScript was cut one by one for each website. And our goal was to answer this question, that for a specific range of memory saving, how much utility does the user need to sacrifice? So the figure here shows the loss in functionality when we make a cut to save a certain percentage of memory. So the x-axis here shows the cuts that save 20, 50, and 80% of memory, and the bar here shows how much functionality do we lose. We see here for a significant number of websites, around 50%, we can trade off 10% of functionality for a 20% memory saving. However, for anything more significant, we do have to suffer from a lot of loss in functionality. We also see that this behavior is very, very website specific. Here's a similar figure for appearance change. We see one difference here as compared to the functionality here. We see that appearance change is less sensitive, so we can make cuts that save much more memory and still suffer little to no change in terms of appearance. Next, I wanted to talk about some of the future work and some of the things that we are working on. So one key thing for WebMedic is to assign user-centric utility to the different JavaScript or different part of the web page. For example, the user might not be interested in the ad, but may be very interested in the headlines. But if you're doing this comparison on the whole page level, you sort of miss this. So for example, for this perceptual hash comparison, it generates a single fingerprint for the whole page. And if only there's a different ad or only if the ad is removed, the hash changes. We don't want that. So we are working on devising a strategy where we can break down the web page into multiple portions or components that we can use for further fine-grained analysis when we are comparing two web pages. We further plan to conduct some user studies so that for each component, we can assign a user-generated weight that can further go into the WebMedic system. Second thing that is working on is a metric for comparison for web pages. So like for performance, we have some clear-cut metrics. We can say that if page load or speed index is better, the page performs better. But now that for systems like WebMedic, when we are modifying the page, we don't have a way of showing how similar the web page is to the baseline or the original one. So for example, in these two examples, the one on the page on the right does not have the ad. From a user perspective, it has all the things necessary. But if we are doing a whole page comparisons, it will lead to very different results because of the ads. But from a user perspective, these pages are exactly the same, and we want to create a metric that can capture that. A third thing that we are working on, it kind of resonates to what Theo was talking about in the last talk, that we want some efficient ways of profiling utility. Website frequently change, and if the website code change, then it means that we need to regenerate our utility profiles, and it's a very time-consuming process because I just mentioned it kind of works as a brute force and does cut one by one in an iterative manner. So we want to generate, or we want to identify some key features of JavaScript that can contribute to utility. We believe that we can use machine learning here if we have a set of features that always contribute to high memory usage. We can sort of use that as a feature to identify the functionality or visual utility of the respective JavaScript. So in conclusion, I would like to say that there's a conflict between device memory resources and website requirements, especially in developing region where websites use tons of resources, but the devices don't have them. Content alteration is the key towards optimizing memory issues, but we need to take care of this trade-off between utility and performance. And now WebMedic takes the first step towards designing an automatic system that can sort of handle this trade-off. We believe that this study can provide the right context for content developers to design their services for the next billion users. With that, I would like to thank everyone for listening to the talk.